So today we're going to talk about trigonometric integrals. Basically, integrals involving sines, cosines, and what have you, in ways in which you cannot use the chain rule in an obvious way. So, an example of integral which you can use the chain rule, and I'm just making this off the top of my head, would be sine to the fifth x times cosine of x dx. Because then here you could just set u is equal to sine of x and du is equal to cosine of x dx, and then you'll end up with the integral of u to the fifth du, which is easy to do. But these types of integrals are different, and there's really not a single way to do them. It's sort of you kind of have to think a little bit. Some of them it's not obvious at all what you should do, and I got a good amount of examples here. This video might be a tad longer than how I would like, but first I'm just gonna do examples. This video's just straight up all examples, different trig integrals. So first one, sine to the fifth x dx. Looks simple, but one thing, do not just say this is. I've seen people do this. It's u to the fifth du. No, that's wrong. The integral we had before would be u to the fifth du, because that would mean that sine is u, and du would have to be cosine of x dx, and that's not in this first integral. So you can't do that. But what you do is you split up the trig functions into functions that have an even power, and then use the Pythagorean identity to replace the sign. And let me show you what I mean. So this will become sine to the fourth x sine of x dx, because we just pull a sign out. And now from the I'm just going to write the Pythagorean real quick. Cosine of x plus sine of x, and these are squared, equals 1. That's what we're going to be using here. So if we solve for sine squared, equals 1 minus cosine squared x. Okay, so now we take this integral, and well, this is sine to the fourth, but that's no problem. We could just write this as sine squared squared. But then sine squared is 1 minus cosine of x. So put that in. From here we can expand. I'm just going to keep this in. It's going to be 1 minus 2 cosine squared x plus cosine to the fourth x. Now we distribute this sign through, and you'll see why we kept the sign. Let me get rid of these parentheses. Okay, now this is the reason why we pulled out one sign and made it even. If this was a 7, we would pull out one sign again and make this to the 6th power. And that's because we used the sign in the du. We make in every single, in this integral, because this is 3 integrals right here. So in this, why can't I highlight this? In this one, obviously it's negative cosine. That one's simple. This one we make u cosine. This one we also make u cosine. So if u equals cosine of x, then du equals negative sine of x dx. So Well, let's just do the integrals. I'm just gonna rewrite them. Rewriting. Integral dx and integral dx. Okay, so here's our integrals. Now we're gonna make the substitutions. This is gonna be u squared from this substitution right here, and this will be u to the fourth, and du, and now we just integrate. There's going to be negative cosine of x minus 2/3 u cubed plus 1/5 u to the fifth. But what's u? U is cosine. So we'll just change this cosine. I used to have a professor says, but we don't care about u. And I thought that was funny because it was a funny pun. Anyway, and let me just check my notes. Oh, there's one thing we forgot. Remember that this is negative sign. So when we make the substitution into the u world, these have to flip signs. That's super important. And people forget it, obviously, because I did. There. This is the correct answer. Double check. Oh, no, it's not. Plus C. Now it's the correct answer. Okay, so that's the first one. Moving on. We just gotta keep this gravy train rolling, because there's a few more left. Alright, next one. Integral sine of 8 x cosine cubed x dx. This one, you again make the powers even. You want to make all the powers even. So I'm just gonna do it right here on the line. You shouldn't do that, by the way. If you're doing it, just make a new line. Alright, so we do that, and then what's cosine squared? Well, cosine squared is 1 minus sine squared, and now we can distribute that through. Sine of 8, and then minus this, minus the sine to the 10th power of x, because you distribute it through, and then the cosine goes to each term. There. Now we once again can use u is equal to sine of x, and then du is equal to cosine of x dx. So this would just be integral u to the 8th minus u to the 10th du, which equals 1/9 sine of, well, u to the 9th, but u is sine, so sine to the 9th x minus 1/11 sine to the 10x. And you know, I'm just gonna write this step in between. So 1/9 u to the 9th minus 1/11 u to the 11th, and then from this step you just replace you just replace u with sine, because that was our substitution. Check the notes. Yep. Alright. Right there. So that one, so basically with these, you want to get the powers even, and then use the Pythagorean identity. That's the strategy to these ones. Make all the powers even, and use Pythagorean identity. You should have one term that doesn't have a power in it, because you take it out to make it even, and that works. Okay, now, next example. we got squared terms in here, and we could try, if we want to use the Pythagorean identities, plug them in, see what happens. But I really don't think that's going to take us anywhere, and it might. But main bullet point of this example is to use these identities. These identities you will use a lot. These two especially, you use these two an unbelievable amount of times. You will grow to know these two. This one not so much, but definitely these two a lot. And they look almost the same. One is a plus, one is a minus. And I was always taught sinus minus the sign. The minus sign is associated with the sign, and that happens a lot in math for some reason. I use sinus minus a lot in a lot of different things, and I don't know what it is, but there's something about minus signs that get associated with the sign. Maybe it's because it's an odd function. I don't know, but sinus minus is gold. Use that and you will remember these two, because you really only need to remember one. Anyway, getting back, we basically just take these two and plug in these expressions right in, and we'll do that right here. Let's get a new line. We got the first one. I'm just gonna paste it right in, and we got minus. Then these 1/2 become a 1/4, and now we just multiply these two out. And if we multiply these two out, we get 1 minus cosine squared of 4x. 4x. Cosine squared of 2x. And yeah, the cross terms cancel. And this is actually my second take on this problem, because I went through the whole problem and accidentally didn't cancel out the cross terms. I put minus 2 cosine of 2x, and I came to the end and found out that I had an extra term. So here I am again. But you know, people make mistakes. You learn from your mistakes, whatever. So now we did that, and let's see here. Now we have a cosine squared of 2x, so we can use our formula again. But remember, the formula is twice the argument. Remember that. So we will use that again. Let's make a new line, and this becomes 1/2, and then it becomes 1 plus cosine of 4x, because 4x is twice of 2x. Now we can distribute this 1/2 through. We get distribute the 1/2 through, and you get this, and then you get 1 minus 1/2, which is 1/2. And now we can factor out a 1/2, and we get 1/8. Now this is a lot simpler. We can simply do the integral from here. So it's going to be 1/8 x plus 1/8 times 1/4 sine of 4x. That's just a simple u sub. And then 8 times 4 is 32, and then you get the plus c at the end. And we check the notes, and let's see, we get minus. I have a minus here in my notes. Why do I have a minus here in my notes? Oh, yes, that's why. Wait, it came from this, and then that goes minus 1/2, and then, yes, this should have been minus. See, I'm going to keep that mistake in here, because people make mistakes. You know, mistakes, a lot of times you watch these lectures or these videos, and the guy does it like perfectly. You know, it's be some wacky problem. It takes like 25 minutes, and like he does nothing wrong. It's because he has the notes in front of him the whole time. But people make mistakes. You know, if you make a mistake, no big deal. You learn from it. And that is the correct answer. Okay. So you gotta get to know these identities because you use them a lot in these trig integrals. And basically, the only way to practice these integrals is to just do a bunch of them. So if you have a textbook, just do like a ton of them, and you'll have it. You'll have it in no time. Alright, so the next one is more formulas that don't come up quite as often. These are the product to sum formulas. Now these come up in a very important topic in math called Fourier series, and these come up in the proof actually for the Fourier series, and extremely important topic in math and in physics. You don't necessarily need to know it to do Fourier series, but it's in the proof, and it's good to do it as an understanding. And it's good whenever I give these formulas or things, I like to tell you that you do indeed use this stuff in the future. So these formulas, not as easy to remember. You know, there's some symmetry associated with them. You got sines here, plus, and then cosines, minus, whatever. You can figure out some sort of symmetry to remember them. But these come up. So we're just going to do one example with these formulas. And in the notes, in my notes, I'm going to use this one. Okay, so we have the integral sine of 2x sine of 5x dx, and that's it. It's a product of two sines whose arguments are not the same. And again, man, this really reminds me of Fourier series, so this comes up. It's a really important topic. So we look at our formulas here. We get the product of two sines there. Arguments not the same, a and b. So we simply use this formula. I'm going to paste it in next to it. So let's make a direct substitution. So we get the we'll type it in right in the integrand. Well, we get the 1/2 out front, and then we get cosine of a minus b. Now a is 2x and b is 5x, and then minus cosine of 2x plus 5x. And you can simplify this to 7, and you can simplify this to -3. Now the cosine is an even function, meaning that I'm just going to do a little aside here, that the cosine of -x is equal to the cosine of x, as opposed to the sine function, which is odd, which the cosine of -x is equal to negative sine of x. So using that knowledge, we could just take away that negative and write it like that. Now we got two simple integrals, so we just do them. Actually, I didn't even need to do that. 1/2, and then we got times 1/3 sine of 3x minus 1/2 1/7 sine of 7x, and then you simplify this. We got the 14 at the bottom, and then this would be 6, and then you get the plus c, and then we check the notes, and it is correct. Yes. Alright. Actually, in my notes, I made a mistake. I'm seeing the notes. I didn't carry the 1/2 to this term. In my notes, I have 1/3. So it's bad. Man, I'm making a lot of mistakes today. So that's that one. Not too bad. It's pretty much use the formula, and you get some simple integral. So whenever you have products of sines and cosines, use the product of sum formulas. These are actually proven in a really interesting way that I don't want to get into, because I don't know if you know the material, and it's just not relevant to this video. So One more equations that you need to know. I'm just gonna write it here. So we have sine. Start off with the sine with the Pythagorean identity. Cosine squared of x equals 1. There are integrals that have secants and tangents in them that you also need to know. And there's pretty much only, when you're dealing with secants and tangents, you'll pretty much only have like one identity, and that's this. You basically just divide this whole thing by cosine squared, and I'm just gonna do it here. Cosine squared x. Oops. Then you get cosine squared x, and then you get cosine squared x. So this one right here is tangent squared x, and this is 1, and this is secant squared x, and this is the identity you use. And actually, in our next problem, we're just going to move this 1 over to the right hand side. So let's do our next problem using this formula, and that it's going to be the integral of secant to the 9th x tangent to the 5th x dx. Now, since our identities are dealing with squared terms, you want to get all the exponents even. So let's do that. We're going to pull out a secant, we're going to pull out a tangent, and then we get secant x tangent x. Okay, now what? Now, in the not so obvious step of, and some integrals aren't generally an integral in the real world is not obvious, and in fact a lot of the times integrals in the real world aren't even solvable by algebra, by these methods. You have to do it numerically. But if you get one that is solvable, it's not, a lot of the times it isn't obvious what to do, and you may need to like, for example, start at this line, switch up secant around, see if you can get anything, do that for like an hour, and say, alright, well, secant doesn't work, obviously, so then you would go to tangent, switch up tangent. When I say switch up, I mean replace with identities, and do some little algebraic manipulation. So in this case, I'm going to skip all the torture and just tell you that you're supposed to, this is the tangent to the 4th, so you change, this is going to be the tangent squared, and then you replace tangent squared with secant squared x minus 1. There. Now, from here, you expand this. That's going to be secant to the 4th x minus 2 secant squared x plus 1 secant tangent, and then we are going to distribute this secant inside, this one only on the left. So this is going to be 12, this is going to be 10, and then this is going to be secant to the 8th x. Now we can, this is 3 integrals, secant 12x times secant x tangent x dx minus 2 secant, and we're not combining the secants for a reason here. You might be able to see it already. Secant x tangent x plus secant dx plus, I didn't do the integral for this one, then plus integral of That's going to be secant to the 8th x secant x tangent x. Now, u, we're going to set our u equal to secant of x, and then our du, if, as everyone remembers, is secant tangent. That's the derivative of secant, the secant tangent. And if you look in our above integrals, we have a secant tangent for every one. And we can use u substitution in all of them. So this is going to change to u to the 12th, and then all this du. And that's, let's move that outside, -2, and that's going to be u to the 10th, and all of this du. And then this is going to be u to the 8th, all of this du, which boils down to 1 over 13 u to the 13 minus 2 over 11 u to the 11 plus 1 over 9 u to the 9, but we don't care about u, we care about secant. So we just we'll just plug secant in, and we will be done. Oops, not sex, secant. Didn't turn it into function. SEC there. SEC. No, SEC. The X is right next to the C, guys. Really. Plus C. You see? Plus C. So let's check the good old notes. Yes, that's correct. Let's put a nice box around it to indicate that that is indeed the correct answer. Okay, that one was tricky and not obvious, but that's just an example of how these integrals can get sometimes. We have the next one is actually pretty simple, and it's an example that shows that all these examples I'm showing you now are not the only way to do these, and in fact sometimes you can't do them like that. You have to be creative. What's the integral of tangent of x dx? Well, someone who just watched this video would try all these identities throw in there, but there's a simple identity here that you can use, and it's just tangent is sine of x over cosine of x dx. And from here we can use a u sub. U is equal to cosine of x, du is equal to negative sine of x dx. So now it's going to be the negative integral of 1 over u du, and that's just going to be negative ln of the absolute value, because it has to be absolute value, because it's the ln, and ln's can't have negative arguments, of u plus c, and which is the negative, I'm just going to copy this so I don't have to get that absolute value, negative ln of cosine of x plus c. And this is what will be in the back of your book or whatever when you say the integral of tangent. And if you want, you can bring this negative. In fact, let me do that. This is the answer. But if you wanted to, you can. Oh, it didn't copy. If you wanted to, you can bring this negative up to here. No, not to there. Up to here because of the rules of exponents, and actually it would be inside that, and then this just becomes secant. But you don't ever see it written like that. So there you go. Okay, we have one more example here, and this one let me just write it. Secant cubed of x dx. Man, does it look simple, but I remember one time I had to do this integral, and like I went through hell trying to figure it out, because I don't know, there was just something about it back then that confused me, but and that's why I'm putting it on this one, because it looks so simple and it's not as complicated as as some of the earlier examples we did. So I don't know why I was confused, but anyway, maybe because it involves a lot of not so obvious steps. So right now, what we're going to do is we're going to use actually integration by parts, and I actually made a video on integration by parts already, and you could just watch that. So first not obvious step, might be obvious now, is switch it up like that. But you're switching this up like you're separating this not for the reasons we had before, but for a different reason, and that's to use integration by parts. So we say u is equal to secant of x. So then du is equal to secant of x tangent of x. Okay, and then we have to pick a dv. Remember, you'll remember that from my video. You pick a u and you pick a dv. Our dv is secant squared of x, and our v is then secant squared of x dx. Yeah, and our v would then be tangent of x. Now we put it all together. We get u times v, which is secant x tangent x, minus the integral of v du, which is secant of x tangent squared of x dx. Okay, that's the first step. Second step, now we replace this tangent of x, tangent squared of x, by secant squared of x minus 1 from the earlier identity, and make a new line here. I'm gonna distribute the secant in. That's cubed, and then this is secant of x, and then I'll distribute this minus sign in as minus plus, and maybe I'll just write this in a neater way, because I don't know, I'm neurotic. There. Okay, now from the example in integration by parts in my video, we're going to do the same thing, and I encourage you to watch the video. And if you don't want to watch the whole video, watch the last example in the video with the e to the x sine, or e to the x cosine of x. Watch that one, because that's what we're going to do, and I'm going to do less explanation purely for time. But it's been said in my other video. So remember that this whole thing equals secant cubed. So now we're going to bring this one over. We're going to bring this integral over to the left, which makes this a 2. And then we're going to divide by 2. 1/2, 1/2. Now, if you look in the back of your book, and I could prove it, but to me, I don't know. Secant of x, the integral of secant of x, it's pretty much one, maybe two steps, but the step that you do is so not obvious at all that I don't know, it involves multiplying top and bottom by something that gives you a u substitution, and you could easily look up the proof. It's a simple proof. It's a couple of lines, and for the integral of secant, and if you're following this video, you will have no problem following that. But that being said, the integral of secant is I can forget if it's negative or positive. It is, I think it's positive, so it's the ln of absolute value. It's like this is how I remember it. The derivative of secant is secant times tangent. The integral of secant is the ln of secant plus tangent. So it's the same thing, same functions. There. That's it. Assuming it's not negative. I don't. Man, my notes are sloppy. So let me just see what I did here, because I don't want to give the wrong I don't want to give the wrong answer, but well, yes, that's correct. If that's leave in the comments if that's not correct, but the only thing wrong about this answer would be this sign right here. So I think that about wraps it up. And as this, I think going through this again, the reason why I had so much trouble with this integral in the past was because, yes, it does indeed involve a lot of steps that aren't obvious. So I think that about wraps this video up. Thanks for watching.